Hey everyone, Mr. Fransky here. Today we're going to do an introduction to transformations of functions. Now this is something you've probably seen before in math class, but it's challenging, especially the first few times you look at it. And the best way to get good at this is to practice it. So make sure you guys are doing the packets that you're getting, you're doing the homework, and then of course following along with the notes and the examples that we're doing in class. So let's take a look at the function we're going to be focusing on today. We're going to use the square root function for all these problems. Square root is a nice function because when you reflect it, scale it, it's really easy to see what's being done to it. Because there's some functions like a parabola. If you have a parabola and you reflect it over the y-axis, nothing happens, right? But square root, you guys probably already know what square root looks like. Square root, I'm going to be kind of intentional about this. I'll put the points on in a second. But square root kind of has a curved shape. It looks something like this. And it's kind of a weird function because the domain is only positive numbers, right? A range goes all the way off to infinity, but the domain is just the positives. But some of the points that are on here we're going to be using, if x is 0, root x is 0, right? What's the next nice number to put into square root? Well, the square root of 1 is 1, right? I plotted that right here, 1, 1. And then the next one that's nice to take the square root of is 4. Square root of 4 is 2. And then the square root of 9 is 3. So we're going to kind of follow what happens to all of those points as we move and stretch and change our graph. So the first one we're going to have here, and you might already know what's going to happen here. If we subtract 3 from the x in the function, you might know how this is going to move it. But I'm going to encourage you to kind of focus on kind of these essential points to the square root function and see what happens to them. So now, if I want to get 0 for my y, what do I have to do to the x? Well, the x that would make the inside 0 here is 3. So I now have 3, 0. So I'm thinking, what x value is going to give me kind of these typical points again? So 3 gives me 0. What would give me 1 now? Well, I need the underside to be 1, so I'd have to go to 4. So I'd be at 4, then 4 minus 3 is 1. Square root of 1 is 1. So I'd be at 3, 0 right here. At 4, I'd have 1 right there. So then to get to 2, I would have to make the underside here 4. So I think I have to go all the way to 7. And then I would get 2, right? Because 7 minus 3 is 4. Square root of 4 is 2. So that'd be like right there. And then to get to 3, I think I would have to be all the way to 12, which is actually off my graph. So it'd be over here somewhere maybe, huh? So what happened to my graph? Well, based on the points we made, it certainly looks like it was shifted right. So I call this a translation to the right. So this is a translation to the right. And notice that it's a subtraction in here. And that might be kind of counterintuitive. Usually we think subtraction, well, that should move things left, right? It seems like something taking away should move something left. But look at what happened. The x values I had to plug in to make the same values appear had to be bigger because we take 3 away from them before we take the square root. So that's why it makes sense to me that a subtraction from the x inside here is going to move all of my values to the right. Okay? So let's see what's going to happen now if we add. This should be the opposite, right? So this time, what x would I need to get 0 under there? I think I would need a negative 3, right? Negative 3 plus 3 will give me 0. And some of you are probably out there saying, wait, I thought you couldn't take the square root of negative numbers. You're right, but I'm adding 3 first, right? There's kind of like implied parentheses in here. So first you add the 3, then you take the square root. To get a 1, I would need a negative 2. How about to get a 2? I don't know why this keeps jumping on me. Sorry about that. In order to get a 2, I would have to have 4 underneath, so I think I would have to have a 1. 1 would give me 2, right? Because 1 plus 3 is 4. Square root of 4 is 2. And then, let's see, to get a 3, I would have to get to 9. So I have to have math in my head. Gosh. I would have to have a 6. Gosh. Okay? So let's plot some of these points. So we have negative 3, 0. We have negative 2, 1. Some people always ask me, can you do this with every function? Absolutely. Anytime you have a thing here, making a table is a great way to kind of get an idea of what's going on. I kind of call it a last-ditch effort. If you really have no idea what this plus 3 does in here, make a table and see what happens. And 6, 3. And there's our function. Didn't quite get through this point, but that's okay. All right. Man, this is just jumping all over the place. So now let's see what happens if the minus 3 is outside. This time, the square root of x is normal. So it should be like back to the regular values that I was taking the square root of, because I'm just going to take the square root, and then I'm going to take the result, and I'm going to subtract 3. So the root x, I take root x of normal values. So square root of 0 is easy, square root of 1 is easy, square root of 4 is easy, and square root of 9 is easy. But now what's going to change? Well, what's going to change is the value after I subtract the 3. Right? So square root of 0 is 0 minus 3 is negative 3. So this time the y's are changing. Notice our y's haven't changed yet. We've been 0, 1, 2, and 3 the whole time because we've been shifting the function left and right. Now we're shifting the function. It looks like it's going to be down. So we have negative 3. When we plug in 1, we get 1 minus 3 is negative 2. Square root of 4 is 2 minus 3 is negative 1. And square root of 9 is 3 minus 3 is 0. So let's plot those points. I don't know why this keeps jumping. I'm sorry. Okay, so let's see here. We have 0, negative 3. That's right there. Then we have 1, negative 2. That's right there. Then we have 4, negative 1. That's right there. And then we go all the way to 9, 0 right there. So that's going to come up like this and keep going like that. Okay. So we see that that subtraction of 3, this looks like it was a shift down. Or I should call it translation because we're going to use S for something later, and I want to keep that language going. Okay. So this is a translation going down. Oops. Cool. All right, well, keep jumping ahead on me. Let's see. So we went down by 3. If we add 3 to the end, so once again, easy to take square root of 0, 1, 4, and 9. So we take the square root of 0 and we add 3, we get 3. Square root of 1 is 1 plus 3 is 4. Square root of 4 is 2 plus 3 is 5. Square root of 9 is 3 plus 3 is 6. So we have 0, 3. We have 1, 4. 4, 5. And then 9 gives us 6. So it's something like this. Okay. So it looks like this was a translation up. So let's see kind of if we can make a little summary of what's happening here so far. So when we had it inside, when it was inside the square root, subtracting moved us right, adding moved us left. If it's outside, subtracting moved us down, and adding moved us up. So often what people say at this point is when it's inside, whoops. So I always say like it's snuggling close to the x. So if it's inside, it has something to do with the x, and it's the opposite of what you want it to be. Right? So adding on the inside moved us left, subtracting moved us right. If it's outside, like this plus 3 is outside of the root, it has to do with the y, and it does what you think. Now, this isn't very deep mathematics here, right? I mean, this is kind of very like informal language saying if it's inside, it does the opposite. If it's outside, it does what you think. But it helps people remember. It helps people remember. But you can always make a table, right? And it makes sense to me that like if it's added, it's after the fact. Like you do the x thing and then you add it after. That's going to move it up or down. If it's with the x, you have to change the x somehow to make it behave like you want it to. So you have to move the function left or right. All right, let's look at a scale change now. Okay, this 2 on the outside. So once again, root x, with the 2 applied later, root x is just going to be normal root values. So 0, 1, 4, and 9 are easy to take the square root of. So square root of 0 is 0 times 2, still 0. Square root of 1 is 1 times 2 is 2. Square root of 4 is 2 times 2 is 4. Square root of 9 is 3 times 2 is 6. So here, notice the x values are the same as they were before. The y values, though, have doubled, because this times 2 out here is going to double all our y's. So we have 0, 0. We got 1, 2. We got 4, 4 up here. And we got 9, 6. So what has happened? It looks like someone grabbed a hold of our function, like maybe with a lasso or something, and pulled it upwards, right? So they took our original function, which was like down here, and they pulled the whole thing up. And that's what that times 2 does there. This is they call it a stretch, and it's vertical by a factor of 2. So they've doubled all the y coordinates, right? Man, scoot, scoot, scoot. Okay, so we have doubled all the y coordinates. We moved them all up by 2. So all those y coordinates moved up by 2, or they doubled, right? All right, well, they want me to move forward. So next one. 1/3, what do you think that's going to do? I think that should push everything down. This should be a vertical shrink. Notice again, it's on the outside of the root, and it has to do with the vertical. It has to do with the y values. So root, again, is going to be normal values, 0, 1, 4, and 9. Take the square root of those, and then divide them by 3. So 0 divided by 3 is 0. 1 divided by 3 is 1/3. Square root of 4 is 2 divided by 3 is 2/3. Square root of 9 is 3 divided by 3 is 1. So we're going to get all the way to 9, and we won't even have gotten out of 1 yet. So 0, 0. 1, 1/3 is about there. 4, 2/3 is right about there. And then 9, 1 is right there. So super, super skinny. I don't even know if I can draw that accurately. Something like that, right? So it still has the shape of square root, but the original square root was up here. We've pushed everything down, right? Everything has been pushed down to be our new graph there. Okay, so 1/3, vertical shrink on the outside there. Now let's see what happens if we're on the inside. So this time, in order to get good root values, what am I going to have to do to my x's? Well, it's not going to be doubling them, right? If you double the x's, then we get them even bigger. I need them to be half. So 0 still work. 2 times 0 will give me 0. Square root of 0 is easy. That's 0. What's the next number that'll work well? Remember, it's easy to take the square root of 1, right? So what do I have to make this x if I want the result in here to be 1? I got to make it a 1/2. So you might already can tell, like, it's the opposite of what we might think, right? We're shrinking our x values to make this work. That'll give us a 1. What'll give us a 2? What would give us a 2? Well, we'd have to have the inside be 4, so I'd have to have a 2 here, because 2 times 2 is 4, square root of 4 is 2. Then to get a 3, I would have to have the inside here, I'd have to have it half of 9, which is 4.5, right? Or 9/2, I'm going to write it as. Then the 2's will cancel, square root of 9 is 3. So let's see what this looks like. So 0, 0 is on there. 1/2, 1 is right there. 2, 2 is right there. And 9/2, which is 4.53, is right there. So now, some of you might look at this and say something different than what I would think. So in here, what's been done is they took our function, which was something like that, and they took all the points and they have been horizontally shrunk. So they've all gone to the left, basically. I would call this a horizontal shrink. Horizontal shrink. Okay, because it's tight with the x, right? It's underneath, so it's doing something to the x's. And we've had to make all our x's half of what they were before. This might be the first time that you might say, wait, it looks like it was stretched up. Well, yeah, you could rewrite this as the square root of 2 times the square root of x. And now, that would be a vertical stretch by a factor of 2. It's the same thing, right? If you stretch something vertically, parabola is a good example. So if you have a parabola, and you stretch it vertically, it would look like this. So you could think about that as a vertical stretch. You could also think about it as a horizontal shrink, right? You can think about it either way. Generally, the way I think about it is if it's tight with the x, I think about it as horizontal. If it's outside, like our last two problems, I think about it as vertical. Cool. Let's see what happens if I have a 1/3 in here. This time it should be the opposite. It should stretch us horizontally. So now what I'm thinking is my x is going to have to be 3 times as big in order to get the result of the y that we want. Well, 0, 0 will still be on there. This time, to get 1 underneath, I'm going to have to make x all the way out to 3, and the square root of 1 will be just 1. To make it a 2, I would have to have 3 times 4, so it would have to be a 12, because then 12 divided by 3 would give me 4, square root of 4 would give me 2. To get a 3, I'd have to have 9 times 3, 27. My goodness, we're not even going to be able to get to 12. So 0, 0, and then we got 3, 1 right there, and then we got 12, 2 is going to be like there, and I can't get out to 27. So it's going to be super stretched out horizontally, right? And again, I'm saying it's a horizontal stretch. You could, once again, say this is a vertical shrink, right? But I'm thinking about this as a horizontal stretch like this. It's taking all those points, stretching them way out to the right by a factor of 3. So this would be a horizontal stretch. Horizontal. Uh-oh. Oh, come on. Horizontal stretch by a factor of 3. Okay. So again, the scale changes work just like we did with the translations, right? If it's on the outside, it does what you think it should do, right? It stretches it up here with the 2, it shrinks it down here with the 1/3. The inside with the x, so it does the opposite, right? The 2x shrunk us down because my x's had to be half of what I would normally have. The 1/3 made us stretch out horizontally because I had to be 3 times what I normally would be. Okay, so I might write that down. So once again, for scale changes, if it's inside, it has to do with horizontally with the x, and it's the opposite of what you think. And if it's on the outside, it has to do with the y, and it's what you think. There we go. Okay. All right, moving on. Negatives. Negatives are special. So if we have a negative here, let's think about this. Once again, my root values should be the same, right? 0, 1, 4, and 9. Those are easy to take the root of, and then the negative will flip it. It will move it somewhere else. So 0, 0, negative 0 is just 0, right? Here I have the square root of the 1 and then negative. That's going to be a negative 1. Here I take the square root of 4. It gives me 2. Then it becomes negative, so it'll be negative 2. Yep. And then at 9, I'll get a 3, and it'll become negative, so I'll have a negative 3. So 0, 0 is on there. Let's see. We got 1, negative 1. There we go. We got 4, negative 2, that's right there. We got 9, negative 3. What happened? What happened to my square root function? It looks like it was flipped over the x-axis. It's flipped over the x-axis. Okay, so once again, it's on the outside here. So it's like, wait, why did it flip over the x-axis? Because it was a vertical change, right? Initially it was up here. Now everything's been changed vertically. It's changed all of my y values. The negative on the outside changed all of my y values. It moved them down. So this guy is an x-axis reflection. And again, I wouldn't think about it as an x-axis reflection. I think all of my vertical values changed, right? All the vertical values were changed. They flipped to the bottom. How about on the inside? What do you think is going to happen here? Well, let's see. This time, my x's are going to have to be what kind of numbers to make this work? I can't take square roots of negatives, so I must have negative x values. 0 will still work, but to make this a positive 1, I would have to have a negative 1, then the negative will cancel out, and it'll become square root of 1 will be 1. So I have 0, 0, negative 1, 1. To make it a positive 2, I would have to have a negative 4 in there, right? Because then the negatives will cancel, square root of 4 is 2. If I have a negative 9, that'll give me a positive 3. So 0, 0 is still on there. Negative 1, 1 is right there. Negative 4, 2 is right there. Negative 9 is not quite on there, but 3 will be right about there. So where we flip this time? This was a y-axis reflection. Because originally over here, it's been flipped over to this side. All of my x values have been flipped over to the other side. So this is a y-axis reflection, but all of the x's have changed, right? So as opposed to thinking about it as a y-axis reflection, you think this negative on the inside here is changing all the x values. So for reflections, if it's inside, the x's change. If it's inside, the x's change, right? So that's really a y-axis reflection, because it reflects it over the y-axis. If it's outside, then what changes? If it's outside, the y's change. So that's an x-axis reflection. And that's really all there is to translations. We're going to get some more tricky examples, but taking the parent functions and multiplying or adding or putting negatives on the inside or outside just does these things. Just does these things to the function. Okay. This is on the first page of the packet that you got today. And some people have all of this memorized. I think this is way too much to memorize. What I just showed you is basically how I do transformations. I think about it as if it's inside, it's the opposite of what I think. If it's on the outside, it's what I think it should do. And if I need to, I make a table, right? That's basically the big thing. But this is really what's happening. If the negative's on the outside, reflects over the x-axis. Negatives on the inside, reflects over the y-axis. Absolute value we'll talk a little bit more about later in class, but that basically takes everything and makes them positive. So if you have, like, if a function looks like this, and this is f of x, then I'm going to do absolute value of f of x. This part that's negative down here will just come to the top, so it end up looking like this. All negative y values become positive. Okay. Inverse, when you switch x and y, we'll talk about that later. Don't worry about it for now. Here, this is where you multiply c times f of x. This is where it's either a stretch or a shrink, depending on if it's bigger or smaller than 1. So if it's a fraction, it's going to divide them. If it's a whole number or bigger number, bigger than 1, it's going to make it bigger. Here's what happened on the inside. Once again, if it's bigger than 1, it's a shrink. Less than 1, it's a stretch. And then here we have our translations, right? If you have plus b on the end, that'll move it up. If you have minus b on the end, it'll move it down. Inside does the opposite of what you think. Plus is left, minus is right. So this is where the rubber band transformation kind of comes into play. If you have a multiple of these things that are combined together, just do RST, reflect. It's written right over there, but I don't write it anyway. Scale. And they write stretch or shrink. I just think scale, because you're scaling bigger or smaller. And then translate. Okay, so reflect, scale, translate. That's RST. That's the order that you can do this every time. Now, the only trick with that is you must have a clean x, and I'll show you what that means in a second. Must have a clean x. Okay, so what that means is if you have something like, I don't know, 2x, well, let's do something else. Let's do 3x minus 9 squared, something like that. Right now, the x has this 3 attached to it. It's not clean. So what you can do is you take out a 3, and you're left with x minus 3 squared. The difference is when you look at this right away, you might think, oh, this is a shift to the right by 9 units. Is it a shift by 9 units? No, it's really just a shift by 3. You have to have it clean before you can look at it, because otherwise, it depends on the order that you do things. In this case, if you didn't want to do RST, if you wanted to translate it first, you could move it 9 units, but then this 3 is going to shrink it back, and it's going to move the vertex of your parabola back to 3. So I think it's easiest just to clean the x and then do RST. So I'll show you that with one example, and then I'll leave you on your own. So all together now. So we got lots of stuff going on here. So the first thing I'm always going to do is clean my x. Okay, and there are some sneaky x cleanings that we'll talk about kind of later in the week. But right now I got that 2 on there. So what I'm going to do is I'm going to pull that 2 out. So we have 2 times x, not plus 4 anymore, but plus 2. And then we have minus 3. So now I write my RST. So my reflection, I see I have a negative on the outside. That means all of my vertical values are going to change. That's an x-axis reflection. So I kind of think about my parent function first, 4, 2, and then 9 up here. And I'm going to reflect it first. So I'm just going to focus on the reflection first. I'll make it red. So just the reflection over the x-axis is going to put me down here. Sorry, I should get those points a little bit better. 4, negative 2, there we go. About like that. There we go. Now so that was my reflection, did that in red. Now let's do in green, we'll do my scale change. So my scale change, it looks like I have a horizontal shrink by a factor of 2. So I'm going to do that in green. So if I have a horizontal shrink, that's going to be at half there. This will be at 2, and then this will be at 4.5, right? Because all my values are shrinking horizontally. They're getting closer to the y-axis. So it'll be something like that. Okay? And now we're going to translate. So I'll translate maybe in purple. So my t, this is, we got 2 of them, right? It looks like we're shifted left 2, and we're shifted down 3. Take some practice, but you'll be able to do this fast soon too. So we're shifted left 2, so that 0, 0 is going to go left 2 right there, and then down 1, 2, 3 right there. So I'm not really going to be looking for specific points. Really what I want to see is that you've moved the graph to the right spot. It's going down instead of up because it was reflected over the x-axis. And then it looks like it's been like horizontally compressed, right? It shouldn't look like the original function. It should definitely look like it's been changed. So often what people do with this is they'll just make it kind of look like this. They'll exaggerate it. They'll make it look even steeper than it really is, right? And that would be fine. I would give full points for that because it shows that you know what's happening to the graph. And that's really the key here is I want you to show me that you know how it's been moved, how it's been scaled. That's the key. All right. So I said there would be some sneaky x cleanings. What if you had something like this? I'm gonna think of maybe like a 1 over 3 minus x. This is a very sneaky one because this negative x, I don't like that at all. So you'd have to clean it like this. You'd pull out a negative sign. You pull out a negative, you'd be left with negative 3 plus x, which I would actually write as 1 over negative x minus 3. So how was this difficult? Well, the x wasn't first, so I didn't see that this is actually a move to the right by 3. You might think this is a move left 3, but you got to clean that x first. So you can see what's going on with the reflection, and you can see what's really happening with the translation. So those negatives, very sneaky. Just be careful about that when you're cleaning your x. So I'd like you to try now is you have this on the front page of your packet. The next 2 pages are all about parabolas. So one of them, you're going to be graphing them. The other one, they give you the graph, and you're going to try to find what the equation is. So one thing to note on that, remember parabolas go through 1, 1, and over here, negative 1, 1. So if you see a parabola that goes through the point 1, 2, like this, what's been done to that graph? And maybe negative 2, 1 over here, negative 1, 2, excuse me. This graph has been shifted or scaled up by a factor of 2, right? Vertically stretched by 2. So just be careful when you're looking at that. And if you look at the key and you get confused, you'll understand what's going on with that because those points, they show exactly where they are. And they're on good grid paper so you can see how they've been moved. So give that packet a shot. Answers are online if you need to check them out. Otherwise, that's all I've got for you. I love you guys. That's why I'm here. Have an excellent day.